Hi, I'm going to talk to you about flavor physics and effective field theory. Effective field theory has its origin in flavor physics, in fact. If you think about Fermi's theory of weak interactions from back in 1933, his theory consisting of these four fermion operators was in fact an effective field theory. And it's kind of remarkable that it was written as one that was just of purely phenomenological origin, but now we can understand it as resulting as an effective field theory in the low energy limit of the electroweak standard model. What I want to talk to you about today is how to use effective field theory to learn a little bit about extensions of the standard model, but in a model-independent way. And that's where the effective field theory comes into play. So let me set the stage by talking a little bit about the standard model, a little bit of a review, so you can set notation, and to talk about the flavor symmetries of the standard model. So very quickly, let me remind you the standard model has fields that are transformed under the SU2 cross U1 of the electroweak theory as a doublet of quarks, two singlets of quarks with hypercharges 2/3 and -1/3. And of course there's the leptons. I'm not going to play a role in what I have to say today, but I might as well write down the complete content of the standard model. And their hypercharges are -0.5 and -1. There's of course the Higgs field, which is a doublet with hypercharge -0.5, and it is a scalar. The doublet I'm going to write down as having two components, which I'm going to label by U left and D left, the same type of labels for the right-handed singlets. And it's very important for us that each one of these objects comes in 3 copies. So there's an index I, except for that runs from 1 to 3. And those 3 copies refer to as generations. Now, the standard model has an interesting set of symmetries. There are only approximate symmetries in the following sense. Let's take, for example, the kinetic term for these doublets. And from here on, I'm going to omit that index I, and it's assumed to be there and it's summed over. This part of the standard model Lagrangian is in fact symmetric under a transformation by a unitary matrix. And while this unitary matrix could in fact be general, I'm going to be thinking of it as just part of the group of special unitary transformations. And the reason for that is that the U1 factor that I could have written, which really rotates all of the quarks by the same phase, turns out to be an anomalous symmetry. So not really a symmetry of this Lagrangian in the quantum case. Now, I could have done the same thing for each one of these fields. So I could have had I would have derived the fact that there's an SU3 symmetry group for each one of those 5 fields. And the whole invariance of the kinetic term would be SU3 to the 5th power. I'm going to be concerned mostly with the first 3 of these. And the transformations that I'm going to use are going to label by the fields themselves. So it's going to be a use of U and a use of D for the up and down right-handed fields. Now, this is not really a symmetry of the Lagrangian, and there's terms in the Lagrangian that break the symmetry, most notably the Yukawa term. Or I should have said the Yukawa term, not just most notably, those are in. So I'm going to write down Yukawa terms for the quarks in a notation in which these numbers, lambda U and lambda D, are 3x3 matrices. And if you write down the most general Lagrangian, those matrices are completely general. But when the Higgs field gets shifted, they produce masses for the terms. And those masses are non-diagonal mass matrices. So it's useful to make a redefinition of the fields to bring those mass matrices into the diagonal form. And in order to do that, what we will do is rotate each one of these multiplets by a different unitary matrix. And when you do that, the neutral part of this term, which is the one that gives rise to the mass matrix for the up-type quarks, rotates as follows. And you can always choose these matrices V sub u left and V sub u right to make this resulting matrix, lambda u prime, diagonal, real, and positive. And so we can read off from that the masses of the quarks, and we can then talk about those three different quarks as different families. And so we will label those as U, C, and T, and for the dime quarks as D, S, and B, once we've done the same transformation. And while this looks a lot like this type of transformation that I was calling asymmetry, it's not really the same. And you see that in that the two components of the doublet are not rotated by the same matrix. And that is the case because in general, these matrices lambda u and lambda d don't get diagonalized by the same set of matrices. So where does that show up in the standard model? Well, any of the other interactions in the model which connect up to up or down to down will automatically be symmetric under these transformations. But there's a set of set of terms in the Lagrangian that connect the up to the down type quarks, and that's the interactions with the charged W bosons. And when you make this transformation, this interaction becomes of this following form. Which involves this matrix, which measures how much we fail to do a symmetry transformation. In other words, by how much these two matrices that transform the left-handed quarks differ. So this matrix we're going to call V, and is the CKM, Kavibo-Kobayashi-Masukawa matrix. And it's not determined by theory. You have to resort to experiment to figure out what the values of these parameters are. We don't have time to go into detail into the determination of the elements of the CKM, but it's going to be useful to know roughly what the values are of the entries. They're in general complex, but I just want to get an order of magnitude estimate. And the diagonal elements are very close to the identity, which means that the rest of the matrix has to be very close to 0. So let me introduce a small parameter of order 10 to the minus 1. And then what is found experimentally is that these two parameters in the 1, 2 block are order epsilon. Then the two parameters in the 2, 3 block are order epsilon square. And then the terms which are farthest from the diagonal are order epsilon cubed. And we'll have occasion to use that in what follows. Now, with that set up, let me ask the question, how can effective field theory help us elucidate something about extensions of the standard model? So let me make a little picture of what I have in mind. I want to have a scale of new physics that I'm going to call lambda that is somewhat above the electroweak scale. So here's the energy scale, here's the electroweak scale, and W, or if you want the electroweak BEV, you can say MW or G2, kind of the same scale. And then there's some scale somewhere around here that I'm going to call lambda. And above this scale, there's some new fields and new particles that we're really interested in finding about. But we're going to try to see what the effect of those particles may be at very low energies. And in particular, at energies below lambda, we can integrate all those particles out, and what we'll end up with is an effective Lagrangian for the standard model that includes the standard model itself, plus higher dimension operators characterized by the scale lambda. So the kind of terms I have in mind are things of the following form, just to give you an idea. Let me pick one. They have to be made out of standard model fields, and they have to be invariant under the full gauge symmetry of the standard model. So let me put in here Q left, sigma mu nu, D right, B mu nu, where B mu nu stands for the field strength of the hypercharged gauge field. And again, fixed generation indices are implicit. And moreover, the Higgs and the quark doublet are contracting a way to make a singlet. So this is an operator of dimension 6, and up to some constant of order 1, naively, the coefficient in front should be 1 over lambda squared. Now, when electroweak symmetry is spontaneously broken and we shift the Higgs field, this is going to give rise to a term that looks like sigma c lambda squared times v times d bar left sigma mu nu d right, and then a linear combination of the photon and z fields, and I'm going to be mostly interested in the combination in the piece that contains f mu nu, and I should include here a cos theta 1, cosine of the weak angle. I'm going to leave it out because it's an order 1 term that I can neglect for now, ignore for now. Now what's interesting about this is, depending on what flavors you have chosen here, this can give rise to a transition that is very interesting. For example, it can give rise to a B2S gamma transition. Of course, I could have written many more terms in this effective Lagrangian, and people have classified all of the operators of dimension 6 that you can make out of the fields of the standard model, and that are invariant under the gauge symmetries. But we don't have time to discuss those 2,500 or so different operators. So we'll just concentrate on one to give an example of how these techniques can be very useful. And the idea is the following. The idea is, given that we can measure a process at low energies and that we have a prediction for it from the standard model, then to the extent that that prediction is successful with some high accuracy, this coefficient in front of this operator or set of operators has to be limited. And from that limitation, we can put bounds, lower bounds on the scale lambda of new physics. So let's see how that works. And I'm going to, in fact, consider this process B2S gamma, which is one of great interest, but also some, fairly straightforward to discuss. Now, as a prerequisite, we need to understand what the standard model says about this. So let me start by writing a diagram that produces this process in the standard model. Now it has to involve a W because, as we just saw, it's only the W interaction that can change generations. But not only does it change generations, being a charge interaction, it changes the type of quark from a charge minus a third quark to a charge plus 2/3 quark. So these virtual quarks running around the loop have to be either an up charm or top quark. Now, I'd like to estimate this, and the first thing of this estimate that I want to focus on is how flavor plays a role. So let's look at these couplings here. the couplings of the W to those quarks. And notice that the coupling of the B quark to any one of these three quarks involves a factor of the CKM matrix VIB, where I is an index that runs over up charm on top. Similarly, the second vertex involves the complex conjugate, because it's a Hermitian conjugate of the term that we brought before, of the CKM. And it involves a stretch core, so it's VIS, where I runs over UC and T. Now, were we to sum over I to get the answer for this diagram, we would find that if we write this in matrix notation, this is the same as V dagger V SB, where S and B stand for 2 and 3, for example. And this being a unitary matrix, this is 1 SB. That's the off-diagonal term of the unit matrix, so this is 0. So that would tell us that this contribution vanishes, but in fact, that's not the case. To get a non-vanishing contribution, we have to keep track of the fact that the quark running around this diagram may have different mass. So the diagram itself will depend on the mass, and I'm going to say through some function that one can compute, that depends on the mass of the ith quark. Now I'm going to make the function dimensionless by dividing by the W mass, and the dimensions for the whole amplitude that are given then by powers of the W mass. So let's consider these. The first observation here is that if I subtract a constant from this function, nothing changes because I just showed you that unitarity of the matrix gives 0. So I'm free to shift this function so that it actually vanishes at 0 argument. And so I'm going to assume that this function has that property and erase this term that I wrote down. The next thing we should notice is that in fact these quark masses are not all the same. In fact, the up and charm quark masses are very small compared to the W mass, whereas the top quark mass is actually about twice the W mass. So we should try to take that into account, and because this function vanishes at the origin, it makes sense to power expand it, to have Taylor expansion of the function around 0, but that only makes sense for the up and the charm quarks, which are very light. So let me rewrite these as the sum over up and charm of VIB, VIS star of MI square over MW square times some number, which is just the derivative of the function at the origin, plus then the VTV, VTS term with this function of MT square over MW square. Now, you could guess that this function, when the argument is order 1, is going to be a number of order 1. And actually, that's what happens when you do a calculation of the diagram. So let's keep that in mind, and then compare the various terms in this expression. Now, going back to our estimate of the entries of the CKM matrix, we notice that the VTV term is order 1 and the VTS term is order epsilon square. And then this function is order 1, so this whole term is of order 10 to the minus 2. However, these terms, for the case of the charm quark, this product is also order epsilon square, and for the up quark, it's actually much smaller. I'll let you check that. But in addition, we have the suppression factor of the light quark mass over the W mass quantity squared. And the charm mass over the W mass is a fraction of order 1 over 50 or 1 over 80, give or take. And when you square that, this term becomes completely negligible relative to the term involving the top quark. So we'll neglect this term. And going back to this diagram, if I only keep here the top quark, you see that all of the particles going around in the loop are very heavy compared to the external particles and the external energies involved in this process. And this suggests that we do an effective field theory description of this process, as we always do at low energies in weak interactions, And so there will be some local operator that transmutes a B quark into an S quark and produces a photon. So let's get an estimate for what this operator would be. Let me call this L interaction standard model effective. Well, in order to produce a real photon, we'll better have a field strength tensor associated with this diagram. So I will put in here a factor of F mu for the photon field strength. And then we have to have a quark bilinear with flavor S bar and B. And to absorb these two indices, I have to have a matrix sigma mu nu. Now, both the B quark and the S quark interact in this diagram via the W gauge boson, and those interactions only involve the left-handed field. So this would suggest that I have to put a left-handed quark in that effective interaction, but that term vanishes because the sigma mu nu matrix can only connect left to right-handed fields. That's easy to cure because you can have a chirality flip at either one of those external quarks, changing the left quark into a right quark, introducing a factor of the mass of the quark. And since the strange quark is very light, we'll do that on the B quark side and call this B right and put a factor of MB. Now this expression that I wrote down has an operator of dimension 5 plus an extra dimension from the B quark mass. So to get the right dimension, I have to put a factor of, say, 1 over mw squared. And to complete the estimate, well, there's a weak coupling constant at each one of those vertices, G2 squared. And in addition, there's a loop and a factor of the electromagnetic coupling. So I'll put in here an E over 16 pi squared. But the most important part of the estimate is what we already did down here, which is a factor of VTB, VTS star, times this function of order 1, which I'm not going to write down because I'm only doing a order of magnitude estimate of the effect. So now we're ready to compare the contribution of the standard model to this amplitude to the contribution of this new physics characterized by this effective Lagrangian. And what I want to do is I want to require that the contribution of the new physics relative to the contribution of the standard model not be larger than, say, about 10%, because the standard model correctly accounts to, say, that precision for the experimental measurement. And I should say very briefly, the full standard model calculation has been done, including QCD corrections, and the corrections are quite large, but under control, order 30%. But for this order of magnitude estimate, this will suffice. So it's very easy to compare these two amplitudes, or even the rates, because the operators that we have in this effective Lagrangian are exactly the same. That means that when we compute an actual amplitude, all of the kinematic dependence will be the same in the numerator and the denominator here, and all that will remain is the ratio of the coefficients. So this is going to be something like CV over lambda squared divided by this whole quantity, E over 16 pi squared, G2 squared, and B over W squared, and importantly, VTV, VTS star. And of course, you have to take the magnitude of this, but when you do that and require that this be less than, say, about 10%, plug in the numbers, you'll find that lambda is required to be bigger than about 70 TeV. Now this is a huge scale. 70 TeV is well beyond what we can imagine doing in a collision at a high energy collider. Certainly nothing we can do now, but nothing we can do in the foreseeable future. So if the new physics is at that scale, we won't have access to it. More importantly, we think there should be new physics at the 1 to 10 TeV scale. And what this is really telling us is that if your new physics comes at the 1 TeV scale, say, this generic operator, if produced by the new physics, completely rules out that model. So that shows you the power of this effective field theory technique. And I want to tell you a little bit more as to what can we do to allow new physics to appear naturally in the 1 TeV range without facing this stringent constraint. And the idea is very simple. If I make lambda much smaller than 70 TeV, I can compensate by making this coefficient smaller. But now I need some reason for the coefficient to be small, particularly in these processes which involve flavor changes, which are really very acute tests of any new physics model. So to that effect, let me introduce an idea that goes by the name of the principle of minimal flavor violation. Let me write that down. And the idea is very straightforward. If you remember, in the standard model, our flavor symmetry, SU3 cubed for the quarks, is violated by lambda u and lambda d only. So the idea is to insist that any new physics model respects flavor symmetry, but of course it cannot respect it exactly because we know it's already broken in the standard model. So we're going to say that the only thing that can break the symmetry is this parameter lambda u and lambda d. But that parameter can appear generally in many places. So to characterize that statement, what we're going to do is we're going to introduce the idea of a spurion. And this spurion is a statement that we can think of lambda u and lambda d as fields, albeit these fields are non-dynamical and they have no space-time dependence. So our term in the Lagrangian that involves the Higgs field and gives masses to the quarks, which we saw is not invariant under the flavor symmetry, can be made invariant now if, in addition to rotating the fields Q and U, we posit that the spurion lambda U also rotates, and now it's a bifundamental under the product group of the two SU3s that we're using here. And so you can see that when we do this term remains invariant. And then the idea of the principle of minimal flavor violation is that we can construct terms in the effective Lagrangian, but they have to satisfy this invariance. So remember we had in our example a term of this form, H Q bar left, sigma mu nu. I'm going to put a matrix here, D right, D mu nu over lambda squared. And I move the constant C to be sandwiched between the two fields, because now we're going to think about this as a matrix. And the matrix has to be chosen to satisfy this principle. So I'm going to give you two examples of terms that can do this. But you could have other terms. Now let's see what happens. I write down this theory in a general basis, and I rotate the fields the up left and down left fields to diagonalize the mass matrix. You can see that in the interaction that we're interested in, that involves here the expectation value V divided by lambda square, and then d bar left, sigma mu nu, and say the first term in this expansion, lambda d times the constant C1. That when we go to the basis of mass eigenstates, this matrix will get automatically diagonalized, and therefore this will not produce any flavor transition, flavor changing transition. If I include the term C2, it will produce a flavor transition, but now the coefficient of that operator will involve lambda u dagger lambda d, which after going to the diagonalized basis will become VIB VIS star MI square over MW square, where these are up-type quarks, and then from I should call V square, and from lambda d we'll get an MB over the dot. And it's now very easy to estimate the effect of this term. We can go back to our previous estimate and just include here the new extra terms, VTB, VTS, MB. What I've done is I've only kept the top quark, which is clearly dominant, and then MT squared over V squared set equal to 1. And we can then ask numerically what's happened to our bound. And you can do the algebra and find that the bound now is 4 TeV. So lo and behold, the scale of new physics is now exactly in the range we wanted. I have no more time. It's been a pleasure. Thank you very much. And fixed generation indices are implicit